Welcome everyone to the Advanced Motion Manager presentation. My name is Marlon Banta. I'm a director in the SOLIDWORKS product definition team. Before we begin, let me note that the presentation materials for the Advanced Motion Manager presentation will be made available through the conference proceedings, and these videos recorded during 3D Experience World are shared via a 3D Swim community after the conference. Also, you can download all the presentation materials, which include the models and this slide presentation, from this URL. I'll pause for a second so that you can write down the URL, but of course I will show it again at the end of the presentation. So the agenda for today's Advanced Motion Manager presentation will be that we're going to review view orientation, and this is something that we covered in the Introduction to Motion Manager presentation. You can, of course, see those materials in the conference proceedings if you were unable to attend. We'll talk about cameras, cameras in motion studies, complex animations with mates, moving assembly cuts and motors, changing the shape of a model using sketch relations and equations in the Motion Manager. And then we'll talk about ways in which you can participate in the development of SOLIDWORKS in our Helping SOLIDWORKS Help You section, and we'll go through some closing remarks. First, let's talk about view orientation. Again, we first discussed view orientation in the Introduction to Motion Manager presentation. And to review what was discussed in that presentation, we talked about two controls that are available in the Motion Manager related to view orientation. First is disable view key creation. When you are disabling view key creation, it means that changes to the view orientation of the model, which is, pan, zoom, and rotate, and perhaps changes to the camera view, will not be recorded as key points in the animation. And that's very important because quite often if you're moving components or selecting components to hide and show or changing their appearance, you inevitably will reorient the model and may not want those view orientation changes to be written to the motion study. The next control is disable the playback of view keys. So if you want, you can disable the playback of view keys so that while the motion study is being played, you can pan, zoom, and rotate. If you have not added view keys, we still have the view key at time 0. And so you'll notice if you have your animation playing back on a loop, it will snap back to the view orientation defined at time 0 unless you are disabling the playback of view keys. The recommended workflow to include view orientation changes into your motion study is to make all changes related to the components first. So that's component position, adding explode steps, hide, show, changing the display mode or the appearance. Make all of those first with disable view key creation turned on, and then make your view orientation changes last. So allow for view key creation and add your view key points to the motion study. One type of view or view orientation is the view looking through a camera. We will first talk about what cameras are and how you use them in SOLIDWORKS. A camera allows you to, one, change the field of view and the perspective. So, here we're looking through the camera as though it were from a telephoto lens, but you can have a very extreme perspective like you'd see through a fisheye lens, and also the field of view. So how much of the model, how much does the model take up the field of view of your camera? If you're using PhotoView 360, cameras allow you to change the depth of field. And so in this example, the number 5 is in full focus, but as you go from 5 down to 1 or from 5 up to 10, you can see that they become more and more blurry. And that allows you to really focus in on a particular part of the model. And that's our depth of field control. Cameras also allow you to fly through the model. So if you have modeled a house, if you're just zooming in without a camera, you never actually go inside the house. But with the camera, because the camera knows its position relative to the origin of the model at all times, a camera allows you to fly through the model as we're seeing here on the left, or actually go inside a model as we're seeing here on the right. So we have the camera inside of that car, and I used PhotoView 360 to render from inside that car. There are many controls for positioning a camera. You can numerically define its position in XYZ space. You can move a camera while editing the camera. You can attach a camera to geometry, and the things that you can attach are the target, so what the camera's pointing at, the camera itself, and then also set the role of the camera. And we'll look at an example of that in a bit. You can move the camera while looking through the camera, and that's different from when you're editing the camera, and we'll see that. And of course, you can lock and unlock cameras so that when it's locked, you can't actually change its position while looking through the camera. While looking through the camera or editing, the controls that you can use to move the camera are rotate, and that uses the middle mouse button, just like we have for view orientation. You can zoom using the mouse wheel or shift middle mouse button. You can pan using control middle mouse button, and you can roll by pressing the Alt key and using the middle mouse button. And those 4 controls are standard with view orientation, and they work in a very similar way with cameras. The one thing that is different with the camera is that you can press Control, Alt, and middle mouse button, and what you're moving is the target while the camera stays fixed in space. And these are controls that you can use to move the camera or the target point either while looking through the camera or while editing the camera. And I'll show you what that means in a minute. So first, we're going to open up this model of the airplane. We're going to go into SOLIDWORKS 3D Experience Connected, and I'm going to open the model from disk. Here's our model. Let's go here to the Display Manager and come over to the View Scenes, Lights, and Cameras tab. While I'm here, I can right-click select to add a camera. This is the Camera Property Manager. If I turn that on, then we can enable the numeric controls, which we'll look at first. So we see that we split the screen in half, and one is the view through the camera, and the other is the camera itself looking at the model. We can change these numeric controls. Let's say we'll set that to 0, make it a little bit more extreme. And you can see that we can move the target point. We can move the camera itself while fixing the target point using spherical controls, or we can move it in Cartesian, X, Y, Z space. And we can also set the role of the camera here numerically. If we toggle between aimed at a target or a floating camera, you notice that this is just a camera that doesn't have a target point. And of course, you can, drag that camera around in XYZ space without a target point. And of course, I can come into this window and use standard view orientation controls to move the camera. So here, I'm basically rotating the camera about the model. I'm using the middle mouse button, zooming in with the middle mouse wheel, hitting Control, middle mouse button to pan the camera. If I press Alt, middle mouse button, there you see I'm changing the role. And if I hit Control, Alt, middle mouse button, the camera stays fixed, but I'm basically rotating the camera about that fixed point. We have controls here for the field of view. In this example, we've set 85mm telephoto lens, but I can set it to be wide angle. And if I zoom in, move the camera closer to the model, we see that the perspective is rather extreme. But if I move it over to, let's say, a 200mm telephoto lens, then we have a bit less perspective. And of course, I can come in here, turn on the controls, drag the aspect ratio of the field of view box. Or I can fix the aspect ratio. Let's say I'll make it a 1-to-1 square. With that, I can move the field of view box in and out. So next we're going to come here and set it to be aimed at target. And we're going to attach, let's say we'll attach the target point to a curve. In this example, attach it to that curve. And then I'm going to go ahead and attach the camera to that point. Let's make that a wide angle so we see more. And then I'm going to set the camera roll relative to the top plane. And you can see that if I move this slider, we're basically moving that target point along that line that we selected. I can also put the camera itself on a curve. So that's not a good curve to select. There we go. We'll select that one. And there I can move the camera as a percentage along that curve. So if I press OK, then we are in that camera view. You can see the camera named right there. And if I try and pan, zoom, and rotate, it says the camera is locked in. Edit or I either have to edit or unlock the camera to allow for movement. And I can unlock the camera by coming to this control here. And now you can see that I'm able to change the position of the camera. And what this does is it actually removes it from the target point and also the camera itself from these curves that I selected. And so those are references that break without causing an error. So let's move on to discussing cameras, to discussing how we can use cameras in a motion study. And so in this first example, we're going to attach the camera to a moving component. And we call this the camera sled example. So here we're going to go ahead and open this model, Jeep through cones. So here's the Jeep through cones example. And you can see that we have a motion study where I've used a pathmate to move the Jeep along this path through the cones. So if we play it back, there we see the Jeep moving through the cones along that path. So we're going to go now and add cameras to add a very dynamic element to this motion study without really changing the position of the components or how the components move through the study. So we're going to come back to time 0. And the first thing I'm going to do is add a camera. And this camera, we want to attach the target point to this point here. And we want to attach the camera position there. And you can see that it's tilted a little bit to the side. And so we want to use the top plane to set the camera roll. And so there we're looking through the camera. And if we play that back, the camera is basically inside the Jeep as the Jeep moves along those cones. Now we can see that sketch for the path. And if we want, we can turn off sketches so that we don't see the sketch as the Jeep moves through the cones. In the next example, we're going to have a fixed camera and we're going to attach the target point to the Jeep. So we're seeing essentially the target point attached to a moving object in the motion study. So to do this, we do need to turn those sketches back on. We're going to come here to time 0, and we'll go ahead and add another camera. Now, in this example, we're going to attach the camera itself to this point, and we'll keep the point that was defined in the previous camera. It's right there, that's fine. And we're going to maintain the top plane for our camera rotation. And so in this example, the camera's fixed, but the target point is attached to the Jeep. So as the Jeep moves through the cones, we see that the camera essentially follows the Jeep. In our next example, we're going to attach the camera to a curve and basically have the camera ride that curve ahead of the Jeep. So if we go back to our motion study, we'll go back to time 0. One thing is I can eyeball time 0 by dropping the time cursor there, or I can come here and move the time bar and dial it exactly to time 0. We're going to come in and add a camera. And this time, we're going to set the target point to be on that curve, and we're going to set the camera itself to be on that curve. And we want the target point to be at 6%, and we want the camera itself to be 1% behind the camera, behind the target point, I'm sorry, and setting that to be 7%. And we'll keep this, this top plane to set the roll, but let's go ahead and modify that field of view a little bit. There you go, it's a lot of perspective. I could say I want that. There we go. Okay, so that's our camera defined at time 0. And what we want to do is come here to time 10, and we're going to edit that camera by changing its properties. And we're going to set the camera itself to 100% and the target point to be 99%. And so when we play this back, we see the camera is riding along that curve, and it's staying ahead of the Jeep as the Jeep moves through the cones. And because we set the target point to be 1%, right, in this case, behind the camera, then the camera is always facing towards that target point. In this next example, we'll look at a free moving camera and how we can just freely move the camera to different positions as the Jeep passes through the cone. So again, we're going to come to time 0. I'm going to set the time bar to time 0, and we're going to add yet another camera. And in this example, it's going to be a floating camera, and we won't have it positioned relative to any reference. And I'm just going to come in here and move the camera and say, we'll set the camera to be, to be up a little bit. And I'm going to hit Control, Alt, and maybe we can, there we go, change the view orientation a little bit. Okay. So that's the position of the camera at time 0. And we're going to go ahead and set that view. And then at time 4, we can come out here and edit the camera. And we're going to go ahead and move this camera a bit. There we go. And at time 10, let's say we'll move the camera to about right there. So what we have is we have 3 points for that camera. And if we play back the animation, the camera is going to linearly interpolate its position between those key points, while linear interpolate its position between those key points while viewing the model. One thing I should probably do is come here and enable view key creation and make sure that I'm looking through camera 4. There we go. And so I was concerned because I didn't see this brown bar behind this change. And so this brown highlight to the change bar indicates that we're looking through the camera, and this blue change bar indicates the properties of the camera are changing over time. So if we play that back, we see the camera linearly interpolating between the changes in position that are defined in the motion study. So the last thing we'll look at with cameras is that, we have 4 cameras defined, and we can change between looking through different cameras as key points within the animation. So if I come here, then we're going to look through that camera. And let's say at time 6, we'll look through camera 1. And you can see this brown highlight to the change bars indicating which camera we are looking through at different points in the animation. So if we play that back, you can see we're looking through camera 4 first, then camera 2, and then we'll transition to camera 1 at time 6. The one thing to note is the transitions between cameras is instantaneous. There's not really a smooth transition between different cameras in a motion study. So next we're going to talk about complex animation with mates. And in this example, we're going to show this product moving along conveyor belts and how we can suppress and resolve mates in the motion study in order for this product to move along those conveyor belts. The recommendation that I would make is to define all of your mates outside of the motion study. You can add mates inside of a motion study that only exist in the motion study, but if possible, add all your mates outside of the motion study and practice suppressing and resolving them before going to define the suppress and resolve states within the motion study. And we'll explore what that means in this example. So you can see that I've added a series of mates, and the ones I'm interested in, I've highlighted them by giving them very specific names. And I've gone in and suppressed and resolved mates as needed. So if we look, I have this mate that keeps the product parallel to that top conveyor. This keeps that parallel to this plane. And I have this mate to keep that edge coincident to the conveyor. And we'll see how that's important in the motion study itself. And then I have these other mates. This makes that product parallel to that slope. This puts that edge coincident to that slope. And this puts that edge coincident to this bottom conveyor. So the motion study that I have defined, I have those mates that we discussed, and then I have these two distance mates. And those two distance mates essentially position the component so that it moves along these conveyor belts. So I'm viewing the model from the top, and we can see that by and large the animation looks somewhat correct, but if I change the view orientation here, it doesn't look correct at all because it comes along this top conveyor and then floats out into outer space above the slope conveyor and these two conveyors. So we're going to use mates, suppression and resolution of mates at key points within the motion study in order to get the product to move along this top conveyor, then slide along this conveyor here, and then ride along these two bottom conveyors. Just one note, I do have a script here and I know exactly the times where I need the mate changes to occur. So if you're ever watching a software demo and they say, oh, I pick a random time, it's generally not random, and so it's certainly not random here. And so the first point in time I'm going to go to is at time 4.5. So I'll just go ahead and move the time bar to 4.5 seconds. And that's where this product starts to move off of the top conveyor and needs to be parallel and coincident to this bottom conveyor. And so what we're going to do at time 4.5 is we are going to suppress parallel to horizontal, all right? And then we're going to suppress the coincident to top mate, all right? Because we want it not to be parallel to this top conveyor belt and coincident to this top conveyor belt. We want it to be parallel and coincident to this bottom conveyor belt. So I'm going to then at that same time come along and unsuppress parallel to slope. So there it is, parallel to the slope. And I'm going to unsuppress coincident to the slope belt. So there it is now, that edge is now coincident to the slope belt. So if I recalculate, we see that it slides along this top conveyor, and then in about 4.5 seconds, switches to that slope conveyor, but then remains attached to that slope conveyor. So clearly we need to have a transition in these mates at a later time. And so that later time is 7.5 seconds. And what I want to do is at 7.5 seconds, it should stop being parallel to this slope conveyor, but still coincident, or still one edge attached to the slope conveyor. And the other edge should be coincident to the horizontal conveyor. So I'm going to come here and I'm going to suppress parallel to slope. And I'm going to unsuppress coincident to lower flat belt. And so there we see that edge is still on the slope conveyor, and this leading edge is now on the horizontal conveyor. And so there we see the product going along that conveyor, then it rides down the slope, and then kind of does that. And so clearly we need to add another mate to make it so that it is parallel to this bottom conveyor. And that change needs to happen at 7.75 seconds, right about there. And what I need to do is suppress the coincident to the slope belt mate. And I'm going to unsuppress the parallel to horizontal mate. And so now when we play it back, we see there that it transitions to be to ride along those horizontal conveyors. And so this is one way that you can use mates to rather exactly position components at different times in the motion study. First, we started with 2 distance mates to have this component move as we desire along the conveyors. And then we suppressed and unsuppressed, or suppressed and resolved different mates at different points in the motion study. You know, here we have those mates that make it parallel and coincident to that top conveyor, then we make it parallel and coincident to the slope, and then we make it parallel and coincident to the horizontal conveyors. Again, by suppressing and resolving mates. In the next example, we're going to look at motors, and we're going to look at how we can use move assembly cuts in our motion study. And we're going to open sharpener and pencil. So before going into the motion study, we can see, let's look at some of the mates that I added. The first is this mate pencil cut. And what that does is it moves this assembly cut feature, which is a revolved assembly cut feature. And when it's at its current position, which is 5 millimeters, when it's at 5 millimeters, it doesn't cut the pencil. But if I move it to 30 millimeters and then rebuild the assembly, cuts the revolve cut cuts this pencil. Let's move that back to 5 millimeters. Go ahead and rebuild the assembly. The next distance mate that I have changes the position of the pencil relative to the sharpener. So here at 250 millimeters, the pencil is outside of the sharpener. And if I change it to 155 millimeters, then we see the pencil is in the sharpener. And so what we want to do is we want the pencil to start at 250 millimeters. So the pencil's outside the sharpener. Come to the sharpener, start rotating, and as it's rotating, we're going to move this cut feature using this mate in order to sharpen the pencil, and then we'll pull the pencil out. So if we come into our motion study, at time 0, we want the pencil to be where it is at 250 millimeters, and then at 8 seconds, we're going to edit that distance mate and set that to be 155 millimeters. Okay. Then we're going to copy the time 0 key point right there. I'm using Control-C, and I'll just put it right there. I wanted it time 12, but I put it at the wrong time to show you that I can come here, and edit the key point time and set it right at 12 seconds. And so what we have is we basically took the starting position of 250 millimeters and copied it to the end. And that's one of the many ways that you can make significant changes to your motion study just by manipulating key points and not really impacting the model. So if we play that back, now we see the pencil exit the sharpener. Okay, the next thing we want to do is we want to animate that cut. And so I've written down here that at time 6.8 is when the pencil starts to go, inside the sharpener. And I'm going to copy the time 0 key point for this mate and paste it, to that time. And so that's a span of time when nothing happens, right? That's a span of time when that cut is not being moved. And having those spans of time when nothing happens is very important, because we don't want the motion of that cut to start until we get the pencil up to the pencil sharpener at time 6.8. And then at time 8, we're going to change this position to be 30 millimeters. Okay, so if we play that back, we see the pencil come towards the sharpener. And then as it enters the sharpener, pencil gets sharpened and then it exits. I could have played with the timing a little bit, but we see the pencil go in, get sharpened and come back out, but that's not really how pencil sharpeners work, right? The pencil has to be rotated. And so in order to get that rotation, we're going to come here and we're going to add a motor to our motion study. And we're going to use this edge to define the direction of rotation. I think that's wrong. Yeah, it needs to go the other way. So it goes into the blade. And so I just go ahead and add that motor. Now the motor is turned on here, and we don't really want that, right? We want to copy this key point and paste it to time 6.8. I'm going to edit the key point time 6.8, and we're going to turn off the motor here, right? Because we don't want the motor, we don't need to be spinning the pencil, I'm sorry, until time 6.8. And then if we come here to time 9.6 or just about, we're going to shut the motor off, and I can dial it exactly into time. Oh, I eyeballed it correctly, 9.6. Okay, so now when we play this back, we have the pencil starting out here, and then it starts to rotate as it goes into the sharpener, comes out as a sharpened pencil. And so that is how, using distance mates and motors, and also an assembly cut, how we can make it look as though that pencil is being sharpened. And so these are the steps that we followed. We attached the assembly cut to a part, and then we could move the part dynamically in the motion study, and we use motors to rotate the part. So the last example that we're going to look at is changing the shape of a model with a sketch relation and equations. And this takes a little bit of it's I would say a little bit tricky to do. This is more of an advanced function within the MotionManager. But we're going to see how we can drive geometry changes using component motion. And so some of the tips and tricks are to move the component with distance mates, to use part level sketch, with relations to the moving component, to use part level equations driven by reference dimensions, which reference the position of that moving component. One thing to note is that it does take a while for this motion study to rebuild. There is a significant cost to doing this. And if you were to export the assembly to an e-drawing and include the motion studies, you would not see this body deformation in the motion study in e-drawings. So here, if I play back the motion study, we essentially see that as we pull back the elastic of the slingshot, not only does the slingshot stretch, but we also see that the elastic starts to neck down as it's being stretched. And let's explain how we set that up in the model. So first, we have this distance mate between, it exists between a plane in this elastic model. So there, it's that top plane, and a plane within the assembly. So that's the first thing that we did. And then if we go into the elastic model, we can see, there's that plane, and this sketch has, an external reference out to the assembly, because what it does is it references, we look at the sketch, it references that right here, that fixed component in the assembly. So we have an external reference, and then we also have here this reference dimension that goes from this line to this point in the sketch. And so as that plane moves, that reference dimension changes. And we use that reference dimension to come in here and drive the equation that changes the cross-section of this elastic as defined by these lofts. So sketch 3 and sketch 8 define this cross-section of the loft. So as this increases, the cross-section decreases. And so again, we have a distance mate, and we have a sketch that references the plane that is being moved by that distance mate, and it references this edge right here that was taken from inside the assembly. That edge lines up with this face. And we use the distance mate to move this elastic back, and as it moves back, the reference dimension in the sketch drives equations that change the cross-section of the elastic. So we end up with a body deformation animation. Again, if we play that back, we can see the distance mate increasing. And because of those equations, we see this cross-section decreasing. I will say that it took me 1 or 2 tries to set this up correctly, but this is how you can change or deform a body in an animation. Use distance mates, and then within the body you want to deform, use a combination of sketch relations and reference dimensions and equations to change the shape of the body over time in a motion study. And what the motion study basically does is it rebuilds the assembly at each point, at each frame in the motion study. To remind everyone that the materials for this presentation and other presentations will be available through a swim community shared as conference proceedings after the 3D Experience World Conference. And of course, you can download the materials for this presentation using this link. Also, I would like to mention that the models that I used in this presentation, many of them were downloaded from 3D Content Central. The F5 Tiger was produced by Matt Lombard, the pencil Ansun Chung Mun Wai, and the pencil sharpener by H. Flora. And these were submitted to 3D Content Central, and I downloaded it from 3D Content Central. Everyone, thank you very much for watching my presentation on the advanced motion manager techniques.